Let's talk about infinite limits. And when we talk about infinite limits, we're talking about where the function is approaching positive or negative infinity as we approach some finite value of x. Recall there are three basic ways that limits fail to exist. First of all, if the limit from the left side is different than the limit from the right, that's the key definition of a limit. So if it violates that, the limit definitely does not exist. A second way is if the function increases or decreases without bound. In other words, if as x approaches c, the function approaches positive or negative infinity, the limit does not exist. The limit is going to be positive or negative infinity. And we're going to concentrate mostly on that one in this section. Finally, if the function oscillates between two values, then it does not exist either. Now, if the function increases or decreases without bound, if both the left and right side of the function approach infinity, then we say that the limit of the function as x approaches c is infinity. If both the left and the right side approach negative infinity, then the limit of the function as x approaches c is negative infinity. So notice when we talk about infinite limits, we're talking about the value of the function approaching infinity or negative infinity. Let's look at a couple of examples of these. In this function here, as we approach x equals 4, from the left-hand side, from the negative side, the function is approaching positive infinity. As we approach positive 4 from the positive side, the function gets smaller and smaller. So it's heading towards negative infinity as we approach 4 from the positive side. It's heading towards positive infinity as we approach 4 from the negative side. Therefore, since it's two different values, the limit does not exist. However, this function here, as we approach x equals 4, as we approach it from the negative side, we're approaching positive infinity. As we're approaching 4 from the positive side, the function goes to positive infinity also. Since those two values agree, the limit as x approaches 4 of this function is infinity. So notice the difference. Here, they're approaching two different values, positive and negative infinity, so the limit does not exist. Here, they're both approaching positive infinity, so the limit is positive infinity. Let's define what a vertical asymptote is. If a function approaches infinity or negative infinity, as x approaches c from the right or the left, then that line is going to be a vertical asymptote of the graph. On those previous functions, we had vertical asymptotes at x equals 4. The vertical asymptote is going to occur where the denominator equals 0. And that occurred in the previous functions too, we just didn't see the functions. Where the denominator is 0, as long as the numerator isn't 0, then we're going to have a vertical asymptote at that value. If the numerator is 0, that becomes a whole. So in other words, look for the zeros in the denominator, double check the numerator to see if it's a whole or an asymptote. If the numerator and the denominator are both 0, that becomes a whole. Let's look at a couple of examples. And vertical asymptotes really help us figure out about infinite limits because that's where infinite limits may occur. If we look at this example, this rational function 1 over 2 times the quantity x plus 1, we have a discontinuity at x equals negative 1 because that's where the denominator equals 0. The numerator does not equal 0 ever, so this is a vertical asymptote at x equals negative 1. On this rational function, x squared plus 1 over x squared minus 1, we have discontinuities at plus or minus 1 where the numerator is going to be 0. We have discontinuities at x equals plus or minus 1 where the denominator is equal to 0. The numerator is always going to be positive, therefore there are no wholes, only vertical asymptotes. So we have vertical asymptotes at x equals 1 and x equals negative 1. And we can't have infinite limits at wholes. We can only have them at vertical asymptotes. So let's look here. The limit of this function as x approaches 1, if we put in a 1, we know 1 is going to be either a vertical asymptote or a whole. It's a vertical asymptote because this does not make the numerator equal to 0. So we know we have a vertical asymptote at x equals 1. We've got to find the limit. Either graph or make a table, so we're going to look at it numerically or graphically and see what happens as we approach from both the left and the right-hand sides. Well, as we approach this function from the right-hand side, we go to, say, from x equals 4, 3, 2, and then we start to get closer and closer to 1. We see as we're going this way, the values get more and more negative. In fact, if you were to put in a 1.1 here, you get a pretty large negative number. So it's going towards negative infinity on the right-hand side. As we approach x equals 1 from the left-hand side, however, the numbers get larger and larger. If you made a table like -2, -1, 0, maybe you went 0.5 or 0.8, you got closer and closer to +1, you'd see that the numbers got larger and larger. Therefore, the limit as x approaches 1 of this whole function does not exist because it's approaching two different values, negative infinity and positive infinity. Let's look at, so you check from the left, check from the right. If you're going to get the same value, either positive or negative infinity, then it has an infinite limit. Let's look at some properties of limits. If we have a function f of x as x approaches c that has a limit of positive infinity, and the same holds true for negative infinity as well. And we have another function g of x as x approaches c that has a finite limit, a value we'll call f. If we combine these two functions, either by adding or subtracting, the limit is still infinity. And the way I like to think about this is infinity plus a number is still infinity. Even infinity minus a finite number is still infinite. The same thing holds true for multiplication. If we multiply two functions, f of x and g of x, that have limits of infinity and L respectively, the limit of the multiple of the functions is still going to be infinity. Or negative infinity in the case of f of x having a negative infinity limit. And one more is the quotient rule. And this is an interesting one. If f of x has an infinite limit and g of x has some finite limit, the limit of x as x approaches c of the finite divided by the infinite is 0. And this is because any number divided by a gigantic number is always going to approach 0. Because f of x is going to get very, very, very large, or very, very, very small in the case of negative infinity. And either way, it's going to approach 0. So let's look at a couple of examples here. If we look at the limit as x approaches 0 of 1 plus 1 over x squared, well, the limit of 1 as x approaches 0 is just 1. So that's kind of like our g of x in the example. Plus 1 over x squared. Well, the limit of 1 over x squared as x approaches 0 is going to be infinity, because 1 over 0 is going to approach infinity. As these numbers get really, really small in the denominator, closer to 0, this part of the function goes towards infinity. So the limit of 1 plus infinity is going to be infinity. And that works either from the right hand or the left hand side. You can check that out numerically, graphically, or analytically, because we have some rules now. Let's look at the limit of 3 cotangent x as x approaches 0 from the positive side. If you look at it, as the numbers get closer and closer to 0, they get larger and larger. And if you picked a number really close to 0, you get a really large number. Because what's happening here, this is the cosine over the sine. As we get closer to 0, the sign of numbers get really close to 0, get really, really small. So that's a tiny number in the denominator, makes this function go to infinity. And that's from the positive. So let's look at infinite limits. Limits that approach infinity or negative infinity as x approaches some value.